So, welcome on my lecture. The lecture is the second part of the lecture I had here last year. It's called The Magic of 256-byte Intros. Today I'm gonna make a short recapitulation of the things I told you last time, and then I will talk about the process, how I write intros, and how I whittle it down to 256 bytes. Then I mix a little how to do it for code and for data, and how to get the high-level intro structure, so that all the instructions are where you need them and they flow nicely. And if we have time, I will show you how to make it look good. So this is a one-page recap of what we done last year. 256 byte intros that I'm talking about are written for PC machines. They actually run even on the newest PC machines when you boot into DOS, or when you load a virtual machine on those. We run in old 16-bit mode from the 80s. We have access to hardware using ports and emulation of old hardware that modern graphic cards and sound cards support. And we have DOS and BIOS calls, which are used to do non-trivial stuff like access different kinds of video devices. For making intros, I'm using an old version of the NetWide assembler, and I debug in Turbo Debugger, which was distributed with Borland C++ 3.1. I prototype in C++ in a way that can be compiled for DOS, and then I can whittle it down the already compiled code, which is atrocious, into something that can be looked upon. In 256-byte intros, we usually use the standard MCGA mode with 256 colors. Each color is 1 byte, which is awesome to access, and we have a palette which we can set at will. Or we can use SVGA with higher resolutions, which is appropriately slower, so it's not very suitable for real-time animations, which we try to make in intros. The x86 processor has 8 basic registers, and in those registers are numbers which are used like global variables. They are available everywhere, and all the instructions with them are really small, because the old x86 processor was optimized for memory accesses, which included memory accesses to code. So the instruction set was optimized for size. So most instructions are 2 bytes, and you can fit only 3 bits for registers in instructions, so they used only 8. The registers we use are 16-bit. We have also access to 32-bit registers, but those have size overhead, so they are not used very much in intros. All the 4 registers which end in X, AX, BX, CX, DX, can be halved. You can use the top 8 bits and bottom 8 bits at once. And use the combined result as the below part plus 256 times the top part. We have access to memory, about 500 kilobytes of them, and we can access 64 kilobytes at a time using a technique called segmentation. There are special registers that are called segment registers, and they specify which 64 kilobyte part of memory you access. For accessing memory, assembler uses brackets as a syntax, and in 16-bit mode we have only a few addressing modes. We can use a few of those registers, the BX, the SI, DI, and BP, and we can combine those two with those two at no cost. So we can do an add moved into the addressing instructions. We can also add small constants, 1-byte constants or 2-byte constants. And what we are not used to in high-level languages, we have access to flags. Almost every instruction set compares the result to 0 and sets the flags according to that result. So we can, after each instructions, we can test whether the last result was 0 by using the 0 flag Z. We can test the sign, or we can test whether we had carry for example, from addition or from bit shifting. The carry and 0 registers are used the most in assembler code. When I talked about memory, I didn't talk about allocation. When we start this tiny program, we have all memory available to us. That is between our segment and segment which is reserved for video memory. So we can simply take the segment our code resides in. We have access to this, and add small numbers to access the segments past that. So allocation is about a 4-byte operation, and we don't have to deallocate anything. The whole memory belongs to us. So last time we also talked about the kinds of instructions we have. The set is pretty non-orthogonal, which means that each register has a special function that only it can provide. There are some nice instructions which take less size, less memory than you could normally await. These I call good instructions. We can increase or decrease a register by 1 using just 1 byte. We can load a 16-bit constant using just 3 bytes into any registers, which is really awesome for setting up constants which you don't have to use memory addressing to access. We can use the Lea instruction which computes the value of this and assigns it to another register without setting any flags, which is awesome to use when you need to keep the flags from a previous instructions and do a small addition. Also, it's one of the few instructions that doesn't have only 2 operands. Normal instructions use only source and destination, and it, for example, adds the source to the destination. And Lea, because it uses addressing, it can add 2 registers and assign to another place, which is normally an operation that needs a transfer. A similar instruction is the multiply by constant instruction, which can take any register, multiply it by a small 8-bit constant, and set another register to the result. This is a way to scale constants. It's a shame that we don't have a division that works like that. We can push all registers at once with the push all instruction and pop them all at once. There's a concept called the stack, which is a part of memory that normal compiled programs use for parameters and local variables. And this 1-byte instruction fills 16 bytes on the stack in a single byte. There's an instruction to convert bytes into words and words into 32-bit words, and there are also instructions that were originally used for BCD arithmetic, but because they have the decimal constant inside of them, we can use them to do small divisions and multiplications of 8-bit values, which is awesome for unpacking small data. Which instructions are bad to use? We can do arithmetic on anything, but if we do arithmetic with a small constant, we pay an extra byte, unless we use the AX register, which is the most used register for this reason. We can do jumps in our code, but if the jump is outside the 128-byte bounds, we pay 2 bytes for the long jump. Calling subroutines has an overhead of one byte as compared to a jump, which is the reason why intros don't use subroutines that much. And all the every 32-bit instruction uses an extra byte as an override. So these are not used either. There are also ugly instructions which force you to use certain registers to keep the size down. You can exchange any 2 registers, but only the AX register uses 1 byte for that. All the other need 2 bytes. A loop is a easy jump that decreases a register and jumps if it's not 0, which is awesome for small loops, but you need to use CX for the counter. There are instructions for moving and loading memory, but they force you to use SI for the source and DI for the index, for the destination. Division and multiplication instructions that make a wide result, for example, 16 bits times 16 bits, which result in 32-bit result, need to use AX and DX. And when you do bit shifting or bit rotations, you also need to use CX. The loop is a misnomer. So this is a really small program. An example. It draws a static image. We fill the register AX with 13 hexadecimal, which is 19, and set the BIOS mode. The graphical mode that we use in most of our intros. We set the screen segment. The screen segment is A000, and use it to write pixels. Then we have a loop which draws 1 pixel at a time. The DI register is used as the screen address. We multiply DI with this constant, which is a constant that turns the width 320 into 256, which is easy to compute with. The result of the multiplication is 32-bit, and the top half, which we are interested in, will be in DX, so we load AX with it. So AX, after this line, contains the Y and X coordinates in the 2 different halves. We subtract them and use the bit exclusive OR operation, which is a really ubiquitous texture because it's really easy to compute. AL is the result. We store it, and we loop forever, because I didn't have time to make a check for escape. But it's customary to include an escape check so that people don't have to restart their computer or shut down the program. Can anyone guess what the result of this will be? Okay. This is the result. We can see the default palette here. When we enter the mode 320 times 200, we have a special palette set up for us. This part, colors from 0 to 15 are for compatibility with EGA. This part is a small gradient, which can work for monochrome intros when you don't have smooth transitions. And then you have almost useless 24 color long parts of HSV, hue saturation of and values. There are all, because these don't fill all the 256 colors, we have a small region at the end that can be either white or black. Some people assume that it's black, and it breaks on some computers. So this is the palette. So how to start making an intro? That's the biggest problem for me. I usually, to do something fast, I usually make a prototype in a hybrid between C++ and C. I don't use a lot of the high-level C++ functions. And I have a simple framework that is similar to the processing or D3.js framework that only draws a function to draw a frame. But because it's so easy to tweak and easy to compile, I spent a lot of time which I should be using to make the intro. So I try to do something else. I've tried compiling for DOS, for the model that supports the file format that we need to use, because the .com file format doesn't have any overhead. It just contains our code and data. So we can use a really old compiler to compile for that, and the output is really bad. It can be cut down to about a fourth. And the good part of that is that we can link the C together with the assembler code we use. So we can iterate a bit on the C side. It's also good practice for optimizing code. Of course, when you have an idea that isn't really suitable for C, for example, it uses properties of certain instructions which have to be emulated in C, it's best to start in assembler directly. When I start writing a program, there's a certain structure I used to follow. I put data before the actual code, but because the program starts right in the beginning of my data, I need to put a jump around it. Later, I always try to discard the jump and try to work around it a different way. For example, executing the data and turning it into harmless instructions. This way, you can turn every data access into an access with a small displacement. You have guaranteed values at the start of the program, and the SI register, which can be used for addressing, contains the start of your program. So the first 228 bytes of your program can be addressable quickly. If you would put it at the end of the program, which is further than the 128 bytes, you would need to spend an extra byte for every constant access. Of course, if you don't use the displacement, you have one particular memory location that is right at the start of the program, and it's awesome to not spend the bytes for that. The +0 here is no operation, and you don't spend any space for that. But at this stage, you don't know what to put there. So I leave it at the end, for the end. I've already told you about immediate constant in the instructions. These will probably be deleted later and reused from the results of previous code. But when I'm starting, I don't have that, so I put the constants in there directly. Of course, when you use FP, floating point instructions, they don't have support for immediate constants, so you have to put them at the start of the program. If you have something big, some sequential data that contains, for example, 30 bytes or 60, it's good to put it at the start of the program because of the ugly instructions that uses SI for loading. So if you have something like that, put it at the start of your data part, and then you can use the modified SI after you load it in for addressing the rest of the constants. What do I do with code? I usually start programming like I do in C with lots of functions and subroutine calls. And also because of the jumps that take 2 bytes when you have a short jump and 4 bytes when you have a long one. When you cut the code into pieces, all of the jumps will be small, so you can estimate the size like that. These instructions I told you about before are used to emulate the standard C stack frame that uses the stack to allocate space for local variables. And also, before you load them back from the stack, you can put other values inside. So this is awesome. It's also one of the only ways how to transfer data between floating point instructions and integer ones. And of course, if you need to use recursion, you have to use calls anyway. So it's good to start at that. But we need to optimize that, start optimizing that when we have something like a working version, because subroutine calls take 3 bytes each. So how to do that? Do fewer calls. I found out that trying to cut it down to 1 subroutine is the best value for the money, because we need, as you've seen before, we need to return from the program when it's not this kind of program. And we need to return from the subroutine. So when we end the program, we just execute the subroutine once and return back to the system. So we save 1 byte like that. We can make one instruction to return multiple things and discard some of them. For example, when we have addition and subtraction, we can just compute both, and usually we don't mind that we have both results if we need only one. So we save on 1 call if we need to use both results. We can put an address of a part of code inside the subroutine, and the subroutine can call something custom that we pass in. The custom thing can be treated like data and put at the start, or you can push it on the stack and call code that is in the stack. It's basically used. Code is basically used like data here. If you do the same calls every time, you can just call once and put all of the bodies at once in one place. So we do the sequence later, and we save on all but one of the calls. Of course, sometimes you need to reorder the calls to get this sequence. When you code in a certain way, you find that parts of instructions can be combined, that parts of code can be combined. So if we take one code that we need and make a subroutine out of it, we can execute just this part or this whole part. So multiple entry points to calls are awesome. And if we put in flags as a parameter, we can branch inside and have two subroutines for the price of 1. How to make smaller calls? If we can't make a call disappear, we can at least make it smaller. We can put the address of the subroutine in a register or at a good memory place like SI, and call using only 2 bytes. but we need to spare that register or memory. So this is not used that much, and you only can use one register for one address. So we can use the interrupt number 3, which is the breakpoint call. This is an interrupt vector which we can reroute, and this is a 1-byte instruction, so we can do a call for only 1 byte. We need to pay about 8 bytes for the setup, and we don't need to restore the interrupt vector at the end of the program, because nobody uses this except for debuggers. However, it's about 20 to 30 bytes slower to do calls this way. So this is good only for preparation and pre-computation, or if you have something like a decompression routine and need to decode bits. So this could be a good place to put the bit decoding. We can treat the calls as data, so we don't need to encode them, encode their addresses. We can just store indices into an address table, and then have an interpreter loop that just takes the index, converts it into an address, and calls the computed value. This is how math-heavy algorithms on ZX Spectrum 256 bytes are made. They use the basic routines for that, and they have a really compact bytecode which has a lot of high-level instructions that not normally available. Also, you can just destroy the calls by inlining each function and noticing that you don't have to move the data around so much. So sometimes you can make it even smaller than 3 bytes this way. When you are done with this and still do not meet the 256 byte limit, we have to use software engineering. So software engineering is about making the code modular and easy to understand in pieces. So we do exactly the opposite of that. Usually we need to cut down on the registers which we use, at least in some places, because it's always nice to have a place to use as a constant, or it's nice to have a register which is suited for a particular instructions to have free. And because it's so suited for this kind of instruction, it's easy to fill it somewhere in and clone it. So in this stage, I'm trying to permute registers and trying to exploit all the instructions that depend on which register are you using. Optimally, when you look at an optimized intro, there is almost no data movement. You always compute something in the place where you will later load it, and in the meantime, nothing disturbs it. Sometimes flags are a good way to cut down on size, but you need to not modify the flags between some parts of instructions. This kind of technique is not really applicable for normal programs, because normal programs have branches, and you cannot do anything between computing the flag and computing the branch without storing the flag. In assembler we can do that, but we have to be sure the flag is not modified. Also, the more complex the idea is, the more problematic is it when you mess it up. So I tend to save a lot in this stage and load old versions a lot. And of course, if you don't have something like write a particular piece of text or draw something database like a picture everyone knows, we can modify the goal and cut down on it this way. The prototype is usually really megalomaniac for that, So we can just cut down on that. So when the code is all done, or meanwhile, when you find opportunities for that, we need to put all the data away. Code is cheaper than data because you don't have to keep an address, and you can exploit redundancies. For example, you don't need to store the sequence 1, 2, 3, 4, 5 if you use it in a sequence. You can just put it in a register and increase it in every loop. You can use recursion in code, which can create awesome nonlinear structures, and most 3D scenes that I have seen are not in 256 by intros, are not stored anywhere. They are just computed from the coordinates that you're testing currently. You can of course use goal description and search some range of values for something that fits the goal most. So you can even do optimizations without storing it first. And of course, you can use random numbers for things that benefit from that and filter them to make, for example, a noise texture or something like that. The intro is always run the same way, and if you depend only on things you are guaranteed, you can have a deterministic intro, even if the algorithm is chaotic. So, for example, if you have some parameter sets that can be unstable, you can tweak the values and then be sure that the intro always runs one way, even if it would break if it would start from a random point, for example. And also, you have some data already available to you. You have values of initial values of registers. You have the DOS fonts, which you can load or draw on the screen and load from the screen. And you have the first, you have 256 bytes before your program, which have some guaranteed values and a nice run of zeros at the end. So if you need zeros for anything, you have 16 bytes before the address 100 hexadecimal. After you're done with that, you can fold the constants. Most of the constants don't have to be exact. You need only a few bytes of them, a few bits of them, or you can have all constants depending on a global scale, so you can move a global scale if you just cancel it out afterwards. Sometimes you can just turn some constants into 0 and 1, which are the best constants ever. And if you have only a few bits, you can store multiple constants in a byte. The same data can be interpreted multiple ways. This is getting a little bit advanced. The basic data format is signed integer, 16, a number between 30K and minus 40K. And most instructions are optimized to be smallest when you use 16 bits. So sometimes even if you have only 8 bits of data, it's hard to do it only in the 8-bit part, and you have to redundantly compute some junk in the bottom 8 bits or top 8 bits. You can of course use only bytes. You can use 32-bit constants, which you usually don't have to store, but you can load them into floating point registers and store them back. So sometimes you can do integer math in floating point in a pinch. You have floating point 32 and 64 bits, and you have bit fields, which are special, which are like an array of 16 zeros and ones. So all of these formats are just bytes and can be reinterpreted as each other. You can some instructions or some contexts use only some part of a register. For example, when you use shifts, only the bottom 5 bits are used, so you can use the top 3 bits for anything else. And when you're setting the palette in DOS, you have only 6 bits of accuracy, and the top 2 bits are also unused. So you can use those top 2 bits for anything else too. When you use floating point, you can use the same constant multiple times. For example, when you put it into sine, it's interpreted as radians. Or when you divide by it, you get 1 over x for free. You have the same constant like that. In some of my intros, I have used an integer for an argument of the sign. I needed a really tiny rotation, so I used an integer number that is really small, modulo 2 times pi. And I also used it for movement, which needed to be large. So I used the non-modulo 2 pi part as a second half of that. And the 1 over x and x trig can be also used in integers, which is the base of the trig we saw earlier, and for having a nice loops of 3. When you do 3D graphics, you usually need to have loops that are executed 3 times and need to address different memory. And this is a really nice trick, which uses a register and at 1/3 that loops over and over itself. So not only can you address three things, do the same things to x, y, and z, but you can also test for the end. So you do it only once. The CCCD trick is basically a 2 to the power of 24 divided by 320, so that when you do 320 steps, you loop over and add 1 here. This is the base of the trick, and it also is an inverted constant, a reciprocal constant. So when we talk about data folding, this is an example from one of my intros. I have a parameter set stored in 1 byte, and it's divided into 3 parts. I use the division and modulo small division and modulo instruction to split it into 2 parts, 2 4-bit parts, and then I add ones here. These ones serve 2 purposes. One is to turn this part into an scaled 8-bit fractional number, and the second part is afterwards I need this one to test to do a loop. We will see it later. So first time I use the most significant part. So I use this thing, and this junk doesn't interest me anymore. Then I use the bottom 5 bits to do a shift So this is like multiplying by 2 to the power of this part. Of this part, this part. And then I shift right, and these 1 bits are used to jump back. They are shifted into the carry flag, and then I test the carry flag. If it's 1, I do the loop again. So after 2 shifts, all the bits are gone, and I can stop. So this is how to pack 3 or something like 4 constants into 1 byte. Compression. Sometimes, for example, when you do music, you have limited ranges of values. You usually play music in a scale, in a vicinity of 1 note. So you have something like +12 and -12 notes. So you have 24 possibilities, and you can pack them into 1 byte again. We've seen that. If you have a really short bit field, maximum 32 bits, we can just store it into a register and shift it out. Or in one of my intros, I used a few 5-bit constants and rotated them 5 bits and 5 bits and 5 bits so that I could rotate a different amount each time. When you shift a register, you set the flags and can use the flags for a switch. So this is a switch based on a few values only. If you have really long bit fields, there's a special instruction that can address by bits in memory. So you can, for example, store a long, like 500-bit field, and use a single instruction, bit test, to get the bit you need. You don't have to shift anything. For example, this technique is used in Crinkler to get the next bit of the compressed data. And nested loops, I told about this last year. When you have a nested loop, you can use the bottom part and top part as two different indices. So you can only use one register without restoring it after each iteration. Compression. If you really need some data, you usually want to contain it the most zeros, or at least small values in the absolute sense. So most values can use differences to put it down. If you have long runs of values or zeros, you can use run length encoding, can load the number of zeros and just generate the zeros you need. You can when you have values in a small range, you can just pack them into bits. I can show you code for that later. When you have long repeated runs of values, you can use something that is used in zip compression, and store a reference to one of the last runs and the length of the run. This can also be used in tandem with the run length encoding. When you have a loop that can transfer bits of parts of bytes, you can point it at already decoded data and have a repeated run, or you can point it at the last byte and have a repeated byte. And when you need to store a set of small values, for example, the first few primes, you can just put it into a register and test for the bit. If it's 1, the prime is in the set. If it's 0, it's not. You can think about compression routines as bytecode interpreters. And you don't really have to use any of those routines. You can just write your own interpreter. So, for example, if you have music and you have long repeated silences, you can put a special code for that. Or when you're making a game of Sokoban and need to store the plan for that, you can just have a big switch depending on whether you got a 1 or 0 bit. And put the least use values to the longer codes. This is something. This is related to gamma codes. And also use explicit data after this stage only when nothing else works, and you have something that you really need to store exactly. You can reduce data even more, because code is data too. Code is just bytes. However, when you interpret data as code, you won't usually like the results. So if you have the data at the start of the program and want to cut away the jump, you have to reorder the data to get something that at least doesn't hurt you. For example, write into memory that is not yours, or set some register that has guaranteed a value and it destroys it, or writes into reads or destroys your stack or whatever. So you can usually do something like that at the end when you're sure that you won't change anything in the beginning. It's much easier to find constants in code. Here are a few instructions that have zeros in them. The addition instructions for 8 bits has a 0 first byte, and you can vary the constant that you get when you read it by using different registers. So AX and AL is 0 in this context, and DI and BH are 7, and the others are distributed evenly inside of that. Remember that the x86 is a little endian machine. So when you read from here, this is the most significant byte, and this is the least significant byte. So when you read this thing, it's 192, and when you read this thing, it's 255, which are both really nice constants. And of course, you can also use constant with the second part, 0. You can get it from using explicit values. Then you have to read the next byte, which will be later here, to get the actual constant. Or you can exploit that some instructions just naturally end in zeros. For example, like this. This is the floating point load, 16-bit load from this particular address. And some instructions make even good floating point values, which is on the next slide. Remember a little endian? So floating point values need the last byte to be one of these values. So you can put anything before that. Usually the first 2 bytes can be treated as noise and can be anything, and the last 2 bytes encode the actual value. So for example, when you have an increment AX, it has this code, and anything with any float with this last byte is a value between 2 and 8, which is a nice floating point value. When you need values that are negative, you just flip the top bit. It's different from integers. So you are almost always guaranteed a return instruction in a program. So you can use it as a constant between 128 and 512. You can also interpret them as doubles, but doubles have a longer exponent part, so only a few bytes are usable for those. Some instructions are some of these codes, like compare AX and the prefix and this that just destroys the AL register. These are pretty much harmless, and you can put them anywhere you want. So this is a way to create floating point constants in code. Okay, let's go away from the compression and look at when to pre-compute, because pre-computation takes bytes to store in the program, and sometimes it's much better to just compute it every time again and again. Also, you don't have to allocate memory for it anywhere, and when you use a floating point result, you don't lose precision when storing it and loading it. So sometimes it's just what you need. When do you need to pre-compute? For speed, decompression is usually done only once at the beginning, and needs a buffer of already decoded bytes. So you would need a buffer for that anyway. But for example, the version of Crinkler for 1K intros takes each output bit and decompresses the whole intro before that for each bit. It's not exactly like that, but it's really similar. It doesn't store the decompressed data anywhere, the decompressed probabilities anywhere. It just computes them over and over. When you have a site that needs to load something, you don't usually have the registers and the resources to compute it. So sometimes it's nicer to just have it in memory and load it. And of course, some pre-computed data like rasterization or smear or most filters. Most filters don't really work that way, and you need to pre-compute them. For example, if the algorithm you need to generate is sequential, but you need random access to the values, you need to store them. Or when the algorithm that generates it is random access, like rasterization, but you need to read it sequentially, you need this too. The inverted lookup table technique is a nice technique how to compute inverses of mathematical functions. For example, if you need a square root table, you can just compute the square and use the square as the index and store the non-squared number inside of it. This kind of thing is a way to emulate instructions that are not available for in the FPU, like arcsine or some cheap approximation to exponentials. So how to make it look well? If you have an algorithm that can accept smoothly varying parameters and it doesn't explode anywhere in the middle, it's really awesome to do animation this way. I use this, for example, in my symmetry intro, which I might show later. But if the algorithm doesn't support that, or it doesn't behave predictably, at least change the parameters in the middle. Sometimes you can use it for having one parameter at a time, then smoothly transitioning to the next one and staying there. It's not really hard to the smooth stair function is not really hard to compute. Also, when you already have a buffer for the screen and you're rendering inside the screen, inside that buffer and not on the screen, it's nice to have a post process, so that it doesn't look that raw. For example, when you have a Z buffer and when you have a depth buffer, Z buffer, and want to display an image using that, it's nice. It can be cool to modify the edges so that it looks hand drawn. Or when you use that buffer, you can just add new things into it and blur the original thing, so that it doesn't look like pixels, but it looks like smears. Of course, when you have only 6 bits of RGB precision, sometimes you need to use dithering, so getting noise from anywhere and random numbers is a good thing too. My favorite types of palettes are palettes that are used for 4 bits for one channel and 4 bits for the second channel. So they have only 16 steps. So I need to compute 2 buffers and then combine them into one, which is also nice for dithering because we have 8-bit precision before the combination, so we can use that extra precision for something noisy. And of course, intro won't win very well if it doesn't run fast on a current machine in DOSBox. So nowadays you don't really need to optimize things for hardware, but for DOSBox. There are things in DOSBox that are faster than in normal hardware. For example, reading from the screen memory, or using the bias functions to plot pixels. These are special cased and optimized, so these are not that bad anymore. Of course, when you want to run it in full speed on real hardware, it's you do the opposite. So something like 2 versions, I don't know. Examples. I would like to show you a few examples that I'm preparing as modular things for new intros. So I will run DOSBox because this projector doesn't support the DOS resolution. Right. So this is a really awesome palette, which has 16 gradients, each one different. This palette uses a technique of storing a bit vector in 16 bits and then rotating it as a multiplier for a really basic gray gradient. So these are just multiplied gray gradients. This can be used, for example, to generate lots of objects, each with a different color. The main problem with this palette is that it's all colder colors. Artistic colors don't really go directly into black, but go there using a less saturated, bluer version. So artists will tell you this sucks, but it's small to generate. This is the same, but it uses 16 gradients in hue. You can see that there are jumps here and here. So it's nice to have small variation of colors. You don't really want to use all the colors at once to get this. This is also really easy to generate with the same technique as before. It's not that similar to the original DOS palette because the original DOS palette doesn't have the lightness steps that you need for colored values. So this is something like fixing the DOS palette. This is the generic 332 palette, which uses 2 bits for blue and 3 bits for red and green. This is the smallest to generate from all of these you've seen now. If you want to turn your intro later into something that generates high quality pictures, then you need to generate RGB values. So this is an easy way to display RGB values in the basic 256 color mode. All of these palette generating routines are something like 8 or 9 bytes, so it's easy to put them at the start of the intro, disregarding the usual thing you have to do when you set a palette. You need to load some registers or use BIOS functions. So I'm not computing these. And my favorites. Time. This is the palette used in the intro Attractor. It's a generic 4-bit 2-channel palette, and it's linear. These are just linear gradients again, which are added together to get the not really wide result. Palettes like this are really good for doing particles. You can do something like cheap gamma correction with particles in that way that when you display a particle on the screen, its color depends on what is already there. So when it's dark, you add a lot, and when it's light, you add only a little, so that you converge to 256 as a result. So this way you can make something look well and have it multiple colors without using colors all over the place. It's best to have a limited palette for these kind of things. And this is just one of the versions of the thing you saw earlier, but the colors are artistically valuable, and the gradient is longer, so you can use that to render smoother things. It's 32 values long. You can also do gradients like this in gamma space when you do a square root inside the palette generation routine, so that you don't have to do gamma correction later. Okay. I would like to show you some intros which I worked a lot on getting the palette right. So I will see into that. However, I don't have a fast computer, so I don't think this will work. Sorry. But actually, I can see the palette here. So this is jeskyně. This is a really simple 128 by intro. It uses 2 linear gradients which overflow into each other. And it uses just one of them. And it uses the artistic trick of not having a normal, not starting from 0. So this is a little blue, this darkest color. I don't think we're gonna get there. But anyway, I will try to make the same trick with pools. All right. Oh, I'm sorry, the first iteration destroys it. So pools in DOSBox here is actually using four gradients, and the gradients are really noisy, and only some parts of these are usable. So the pools intro, which renders a 3D scene with four colors, actually uses only something like 40 colors in total. So you can see here that the start of dithering, which is more like glitch noise in pools. However, the palette is really easy to generate, and it also doesn't use coder values, coder colors for these. So let's kill it again. Right. When you don't have time and space to get a good palette anymore, you just need to use the old DOS palette. So the old DOS palette has those two parts, one of these and one of these, that can be used nicely in tandem. This 16 color part is also a nice way to test those 4-bit palettes which you saw earlier. So you can render without setting the palette and just adding 16 to get to the gradient. And later, when you're having fun with palettes, you can use a 4-bit palette, and you have the code already for that optimized. So this looks like it's the end. Are there any questions, or do you need anything from me anymore? If you have particular questions about some of the things I've talked about, you can just find me here, and we can chat afterwards. So if there are no questions, I will end the lecture. Thank you for listening.